So mixing is a lot more of a complicated science than people give it out to be. And I know this might sound strange, like you mix in the you mix in your kitchen all the time and all these other things. But no, it is really, really complicated. To give you some ideas of the complexity, is first of all, you have if you just move water or liquid or anything just back and forth, you can move big large chunks of it, and you waste a lot of your power and time it takes to mix stuff. Imagine, to give you an idea about this, imagine if you have a room and the room is filled with two rooms actually, one room is filled with blue balls and one room is filled with red balls. If I just take all the bunch of red balls together and move them, and a bunch of blue balls together and move them in one big chunk into the rooms, I'm not really mixing well. But if I randomly throw one ball at a time from one room to another one, I get mixed in pretty well. So big blades might not be the best at mixing it, but big blades also might work better because they move bigger chunks from a vaster distance. So you have that problem, and you can waste a lot of energy, or it can just take you a lot longer to mix it. The more energy you waste, the more heat you create, and more you might actually destroy stuff in your mixture, or and longer you take it, the harsher condition, the more you might destroy something sensitive in your mixture. Another problem with mixing is that it can generate heat. Now, heat can be very useful in mixing because things tend to dissolve better in higher temperature things, with a major exception in gases, in liquids, because gases kind of just boil off, or gases in solids. And gases also, when a liquid becomes less viscous, they can also more easily rise out. So gases are the major exception, but everything else, pretty much it's true. But heat can destroy delicate things, and it can also waste power because it might not always be the most efficient way. Heat also means you have to cool it down afterwards, which can waste more power cooling it down unless you naturally let the heat go. Now, if you naturally let the heat go, you could use heat recovery systems, or you can cool it down faster with a heat pump, which is like the reverse of an AC. A heat pump is like some heat exchangers to cool in the incoming stuff and outgoing stuff, but that all gets more and more fancy. So yeah, then you have this heat thing. You also have shear forces. With shear forces, are forces that top or bottom, or in two different things that slide in opposite directions, like here. So if it was on a human being, if I was holding your arm and someone else was holding your other arm, and I was moving to the left and they were moving to the right and you were stuck stationary, that would be a shear force. Or if we're moving in opposite directions, but sideways. We're not stretching you out. We're not stretching you out by pulling you apart by your arms in the same plane. There's a separation. Not the best explanation. The better one is that it's something that kind of would turn the object. Shear forces can turn the object. Now, shear forces can be useful in mixing, but they can also rip stuff apart, and especially delicate structures or molecules that are delicate and big. They can also cause excess heating or differential heating. Differential heating in something can be very bad, because differential heating can cause stuff to change shape more rapidly, which can cause more damage to like proteins and delicate structures. It can cause heat loss. It can make it harder for instrumentation to gauge the temperature of the whole thing, which can make it a lot harder for it to keep everything balanced, because one place might be a lot hotter than another place, so it might start cooling, but that might cause another place to get too cold. It can make heat exchangers more complicated. So that's the big overview of mixing, which is one of the most important things in making new drugs in the massive size. And pharmacology, it's very important in making plastics and much more. So how do I propose maybe we can get a little better mixing? Now, the first part has been something widely done. So, and that is what a lot of people have done in the past is mixed by putting a lot of bubbles into a liquid. Now, these bubbles have a lot of advantages with mixing, because the bubbles are tiny little things, and they mix by first of all, pushing water as they go up, or any direction, they push water aside, or any liquid, mixing it. But then when they come back, but then the liquid around it comes back down and mixes as it gets pulled back together in different ways, and that causes little mixing everywhere. And because it's a little bit of mixing everywhere, it can be a lot more gentle than a big mixing thing that has to move really fast on the outer tips and it's moved slow in the middle. If you imagine something turning, it's not turning as fast in the middle as an outer one that has to cover more distance, and it doesn't have to. It's not moving as big chunks of water, so it's more thoroughly mixed. Now sometimes you want to move big chunks of liquid or water. I should stop saying water, I should say liquid, because you want to move the big chunks from all one side containing another one. But you can move that in little chunks over the place. It's probably a little better than just grabbing and forcing it. This means that you can also get less heat problems, dissipation, and many other things. And it can be more energy efficient in other ways. The problems with it is that once it bubbles out, you don't have the continuous momentum of the blade continuing to do it. But that's also kind of good sign, because also you've lost a lot of your energy. And it does also lead to more even heating by the bubbles just naturally carrying a lot of the heat up and down throughout the entire system. Now, if you add a propeller or some mixing stuff, which we can use a propeller or we can use ultrasonic waves, we can make this even more efficient, which a lot of people have done. And that is because the bubbles can be now move in more directions. So if you have that effect, they might be moving up even faster throughout the liquid, or they might be moving side to side, mixing it, or in other directions, or zigzagging, mixing it even more thoroughly. Then the other thing they can do is that they can change the shape of the bubbles, split them together, or merge them, or just stretch them and de-stretch them, which causes more vibration and local mixing, making this whole thing even more advantageous. Now, you have to be careful with this, because you can get effects where you get locally a lot of energy, where if a bubble splits and then collapses back together, or stretches and collapses together, it can actually release locally a ton of energy, which could destroy delicate things. So this is actually a careful balancing act. If you want to see cool pictures of it, I would recommend looking up something called sonoluminescence. Now, so far, I think we're pretty good. But what they recently discovered, and also it doesn't have to be mixed, we can also use ultrasonic waves to help it mix too, with bubbles recombining, decombining, and moving around and stuff, is they've recently discovered that when you take a liquid and you pump out a lot of the air and gases in it, it suddenly becomes, oil and water can mix they almost can mix if you take it really regularly. It takes a lot longer time, and stuff normally can mix well. We don't fully understand the effects. We think a part of it might be that there's that air bubbles formed at the interfaces of the liquids and help stabilize and they pull stuff together and destabilize it. But we really don't fully understand it. But it has been in repeated trials, and people observed it at their homes. Now you might be like, oh, there's no air and water and stuff. There's a tiny bit of dissolved gases in every single piece of water you drink almost, and we can pump it out. However, how would putting bubbles in something pump out the air? Well, it's a common way of pumping out a lot of the air is using bubbles, and that's because different gases dissolve to different extents in a liquid. And nitrogen, for example, with these gas, dissolves about half as much as oxygen in water. So if I have and even less than half. So if I pump in nitrogen, what happens is nitrogen doesn't dissolve in the liquid as much, but some of the oxygen goes into the nitrogen bubble and comes out. So then you slowly start pumping out the oxygen. Now, if the nitrogen bubble is hot, you can, and maybe you cool down the liquid and keep the nitrogen hot, which is a little waste of energy Depends on the use and how I want to do it, but this opens up more possibility. Then you can heat up the whole liquid while pumping out oxygen. And again, remember, oxygen does not, gases drop dramatically in how much they can dissolve in hot liquids. This is a very rapid way of also heating up the whole liquid evenly because you're pumping out a gas. Nitrogen I use as the first example because it's very, very cheap, and it is something you can get from the air with a purify it. And that means you can take the nitrogen out of the loop and purify again and again. It's also not inert and it's pretty darn safe. The only major problem is you asphyxiate on it, or you just breathe in nitrogen and you don't have enough oxygen. But your body usually can sense that. And also nitrogen is something that can easily exit your body, unlike some other gases which you can asphyxiate on. A much more expensive alternative would be helium, which has super low solubility in water and in many liquids, even wider range than the other one, because it has almost no interactions with other things. It's a noble element. Now, a lot of noble elements have very low interactions with it, because you can look at this chart too, that you can use other ones. Now, here's a problem. Helium and a bunch of these gases are a lot more expensive. So if they are easier to handle and bubble, and equipment to handle it will be a lot easier because they are easy to dehumidify and remove the liquid later on. They are very safe to use, but you have to figure out some way of recycling and keeping it in the closed system so you keep pumping out the bubbles you pump in, perhaps by putting lower atmosphere above the whole liquid, which would pump out even more gas faster and cause a solubility mix. But a low atmosphere above might not be the best when you're dissolving certain chemicals and might make some of the liquid evaporate, which may or may not be harmful, and you might need to recondense it with special condensing foils. So it's not that simple. Other noble elements are not as great as helium, and sometimes they're cheaper, sometimes they're more expensive. Another problem with helium is that it leaks very easily. Because it's so small, it's actually a lot harder to make stuff airtight. But that's also with every inert gas also leaks more easily because it doesn't stick to stuff as well. So pros and cons, and maybe you start mixing it first with regular bubbles, then you mix later on with nitrogen, and you mix it with helium at different stages. And nitrogen and helium can separate out pretty easily. So only in the last stage do you really have to worry about this whole procedure. Well, thank you very much for listening. Please like and subscribe. It really helps the channel out. I'm trying to reach 1,000 subscribers in a year and 4,000 watch hours, which is really hard. With your help, I think you can do it. Also, if you have any ideas for future videos, comments, or suggestions, please leave in the comment section below. Again, thank you very much.